Hello everyone, welcome to OneClass's online math session. My name is Bassam, I'm an engineering graduate and I'm going to be guiding you through some popular math questions and questions proposed by you guys. We're also going to be verifying some proposed solutions. So we're going to start off here. So these questions are math questions from the high school and the preliminary college level. So the first question we're going to be tackling is as follows. Which complex number has a distance of 13 from the origin on the complex plane? So I think in this question there's a typo. This should be square root 13 based on, so based on the provided solution, I believe there's a typo in this question. It should be which complex number has a distance of square root 13? From the origin on the complex plane. So usually we can see that from the answer choices provided, they're in the format a plus bi. So a plus bi. So in the first one we have 4, and then 4 equals a, and then 9 equals b, and so on for the rest. And we're going to be using these two values to determine which one gives us the distance of square root 13. The basic formula for calculating the distance, so here we'll represent distance as r, and we know that r squared is equal to a squared plus b squared on the complex plane. So this is a standard formula for calculating the distance between the origin and the point on the complex plane based on the a plus bi format. So we'll start off with the first option. So let's go back up here. We'll start off with option A. So we have A. A is, we have r equal to the square root. So a squared, which is 4 squared plus 9 squared. This will give us square root 16 plus 81. And if we add these two values together, we will get square root of 97. So we can eliminate answer choice A because we did not get square root 13. Our goal is to get square root 13. Go through answer choice B. So B here is r is equal to the square root. So a is equal to 2 in answer choice B, so we have 2 squared plus, and then b is equal to negative 3, so negative 3 squared. This is all square rooted. So we get 4 plus 9, which will give us square root 13. Okay, so we see that answer choice B is the correct answer. We're going to go through C and D just to verify that only answer choice B is the correct answer. So C is r is equal to the square root. So here we have 15 and 2, so 15 squared plus, so negative 2 actually, negative 2 squared. Here, regardless if it's negative or positive 2, we'll still end up with the same magnitude value. So here we get, so here I'm just going to plug in square root the 15 squared into the calculator. So 225 plus 4. And we can right away see that this is not going to be square root 13, so it's 229. Okay, so I'm just going to erase a portion of the board to do, okay, we'll do the last one, which is D. Okay, so So D, we have R is equal to square root of A squared, which is -1 squared, plus -12 squared. This will give us square root of 1 plus 144, which will give us square root 145. So we've confirmed that none of the answer choices are correct other than B. So here, let's look at the solution proposed. So, yep, they go through the same formula. This is mainly, so here they have C and A here and D and B. So if we had 2 points, if it wasn't from the origin, then this formula would be useful. But since we're looking from the origin, the distance from the origin, we can just do A squared plus B squared, all square rooted. So yep, they have the same answers, and then they selected B for the correct answer choice. So solution is correct. Great job. So here we're asked, what is the magnitude of the cross product A cross B? So A cross B. And we're by putting the arrow on top of each variable, we're classifying these as vectors. So for each vector in a 3D plane, there's 3 components. There's the x, y, and z. So we can define this for each component. So we have A is equal to, we have A1, this is the magnitude, and then the direction. I is in the x direction, plus A2 times j, which is the y direction, plus A3 times k. So we split up the vector A into its 3 components in the x, y, and z direction on a 3D plane. And we'll do the same for B. So B equals B1, I plus B2, J plus B3, sorry, B3K, not J. So these are kind of the separate components for each vector. And this will help us figure out the equation for the cross product. So here we'll do A cross B. A nice way to look at this is to draw the following. So we'll have I, J, K, and we'll have A1, A2, A3, and then B1, B2, B3. So putting it in this kind of matrix will help us derive the formula for kind of the magnitude. So to start off, to look at each component, so we want to solve for each component of the cross product, the I component, the J component, and the K component. So we know here, let me just erase this, so we'll move the equal sign down here, so equals. So when we're calculating for the I component, what we want to do here is we cover up this, or let me rephrase that. We would look at only this part. So we don't look at the column I. We only look at whatever else is not in column I. So looking at just what's not in column I, so we have A2, B2, A3, and B3. So to calculate the I component, it's basically the cross. So A2, sorry, let me redo that. So A2 times B3 minus B2 times A3. So just thinking about it as a cross, that'll help you derive the equation. So here we have the first component, A2 times B3 minus, we have B2 times A3. Okay, I'm just going to double check something really quick. Good. We're just double checking that we are on the right track. So here we have the I component, and then we do the same thing for J and K. So in scenario J, we ignore the J column. So we're going to ignore this column, and we're only going to look at, I'll highlight them in red. So we're only going to look at this column and this column. And what we're going to do, we're going to do the cross. So A1 times B3 minus B1 times A3. So we'll write that out. So we have A1 times B3 minus B1 times A3 is J. So that's the J component right there. And now we have the K component, so the component of the vector in the Z direction. So we do the exact same thing again. We ignore the K column, and we only look at everything else, essentially, except for the K column. And we do the cross, so we'll do A1 times B2 minus B1 times A2. So I'll write that out. So we said A1 times B2 minus B1 times A2, sorry. So now we've defined each component of the cross product in terms of A and B, in terms of the two vectors that we're using to complete the cross product. And then here I'm going to erase the top of the board, but we just really need the bottom section here to derive the magnitude. So the magnitude of the cross product here so the straight lines on each side is a reference to the magnitude, is basically the square root. So the magnitude of the x component squared, so I'll represent that with, I'll just say, so we're talking about the magnitude of the x component squared plus the magnitude of the y component squared plus the magnitude of the z component squared. Okay, so this is just the basic magnitude formula where we have the square root of each component squared. So I'll erase what's in there and we'll fill that out based on what we've calculated here. So this is all underneath the square root. I'll put it in a large bracket. So the first part is A2 B3 minus B2 A3. And this is the first component squared. And then we add on A1 B3 minus B1 A3 squared, and then we add on A1 B2 minus B1 A2 squared. So I essentially just took the x component here and used it up here and squared it, and then the y component here and used it up here and squared it, and then the z component here and used it up here and squared it. And then this equation right here, this equation gives us the magnitude. So you don't see the top portion because of my face, so let me see if I can drag this down. Okay. So I don't think you see the first portion. So the missing portion, I'll just write it out. So it's just the first term, this term, I'll just write it out down here, is A2 B3 minus B2 A3 squared. So that's just the first line up there, and then the rest is visible on the screen. And that's essentially the formula for the magnitude of the cross product. So here we can see they followed this similar idea, and we just kind of gave you a further explanation of how to derive that formula. Okay, so here the solution is correct. Okay. Okay, so the next question that we're tackling is a number line question. So which number line represents the solution to the magnitude of x plus 4 is equivalent to 2? So here we have the magnitude of x plus 4 equals 2. We want to see which number line, and it's giving us 4 options here to select the number line that represents this. And we can see that each number line has 2 dots. So looking at this, whenever we're kind of given magnitude on the left side, especially when the function is inside the magnitude lines, we essentially just need to evaluate x plus 4 equal to positive and negative 2. So in the first scenario, we have positive 2, and then in the second scenario, we have x plus 4 equals negative 2. So just from the initial equation, we're able to derive kind of two equations that we're going to use to define each point on the number line. So solving the first equation, we just subtract 4 from both sides, and we end up with negative 2 here. So we have 2 minus 4, which will give us negative 2. And then here we subtract 4 again from both sides. So we have negative 2 minus 4, which will give us negative 6. And then looking at each number line, we have the first one gives us negative 2 here and negative 6. The second one gives us 2 and 4. Third one, 2 and 6, and then negative 2 and 4. So here they're trying to trick you with the 2 and 6 here, but we know that it's a negative, so we know it's the first option. And looking at the first solution, the solution provided, they also select the first option and do the correct process to solving this. So this solution is correct. Okay, so the next question that we have over here is, how do we write 1.5 million in numbers? So I'm assuming this is asking us just to write kind of all the zeros associated with 1.5 million. So here, 1.5 million, this is a dot, or a decimal point, in kind of the full kind of numerical way. So we can start off with a simpler number. So we know 10 is 1 0. So this is 10. We know 100 is 2 zeros. Oh, sorry for the, so this is just 100. And then we have 1,000, which is 3 zeros. So, oh, whoops. Okay, so I think we get the gist here. So this is 1,000. So knowing this, we can go further. So we know 10,000 is 3 zeros. I'll put a comma here so we can see the number of zeros. And then 100,000 is 5 zeros. And then from 100,000, if we add one more zero, that gives us 1 million. So this is 1 million. So knowing this, we kind of started out from, the simpler numbers that we already know, 10, 100, how many zeros, and built off to get to figure out how many zeros are in a million. So from here, we can multiply 1 million by 1.5 to get our solution. So if you multiply this by 1.5, we essentially have to move the decimal point whenever we're multiplying by 10 or multiples of 10 with many zeros. We count the number of zeros here, and then we move the decimal point over by the number of zeros. So here we have 6 zeros, so we have to move the decimal point over 6 times. So here, I'll remove some of the stuff up here. So we have 1.5, 5, and then we're going to move 1, 2, 3, 4, 5, 6. And in each spot, we're just going to add a 0. 1, 2, 3, 4, 5. So here, we only add 5 zeros because the first 0 is accounted for in moving the decimal place over the 5. And knowing this, since now we've moved the decimal place over, now the decimal point is at the end. You don't necessarily have to write it, but just to tell you where it is. And we're left with 1.5 million, but in a numerical format. So we can put commas between every 3 digits just to make it look a little clearer. And this is our final solution. So this is 1.5 million in a numbers format per se. So here, looking at the solution. So they've given a similar solution. They've separated out their commas a little differently, but they have the correct number of zeros. So they have 5 zeros and then 15 in the front. So usually when you put your commas, you do them between every 3 digits to kind of account for every 1,000 multiple. Okay, so we finished solving this question. All right, so on to the next question. So this isn't really, let's see what the solution says, because the question isn't said here. So it looks like this question is just inferring from the solution here. It's asking for the square root of 16 square root of 1600 in its simplest form, or what is its value essentially. So here we can start off by thinking of ways to get the factors. So always when you have zeros in a large number, just start off with those. Those are the easiest. So we know that 1600 can be split up into 16 times 10. That's for one zero, and then times 10 again for the other zero. And we can split this, we can also simplify this, knowing that there's two 10s. That means it's 10 squared. We can take the 10 out front, so we're left with 10 square root 16. And we know that the square root of 16 is 4. So here we would have times 4, which would give us 40. Because we're doing a square root, whenever we're square rooting a number, usually we're taking the positive and negative value, depending on how the question is asked. So if it gives us, x squared equals 1600, and we have to solve for x, then in this scenario we'd say the answer is plus or minus 40. But if it's just asking us for the positive square root of 1600, then we can just say the answer is positive 40. But here we don't really have a question. We're kind of just inferring based on the proposed solution. So the proposed solution follows a similar way. So they split it up into factors of 2 and simplify it down until they get to the smallest number they can get. So here they use a different process to get the same answer. Usually this is based on preference. So yeah, they also have positive and negative, so I guess this is more based on the question. And they give some more examples of how to do the square. So they give you the square root here of 4 is 2 squared square rooted, and which will get us 2. And similarly with 9. So I believe this process that I did is a little more straightforward. So this might help you out here, where you're not necessarily dividing 1600 by 2 multiple times. You kind of split it out into simpler numbers that are more easily understood and easier to divide out. So this is the correct solution. Okay, here the solution is correct. Okay, so we're asked here the following. So we have a function f at x equals 1 minus x. And we're asked to find the value for the magnitude of f at I. So here x is equivalent to I. So I is an imaginary number, and I is equivalent to the square root of -1. So since we can't really square root -1, we define it as I as an imaginary number. So using this, we can go on to substitute I into the function. So we have I is equal to 1 minus I. So this is kind of what f at I is, and now we need to evaluate for the magnitude of I. This 1 minus I. So we recall that A plus B, that's an ugly B, so B I. So the magnitude of this standard equation is A squared plus B squared all square root. So we know this is the magnitude for any equation that is in this format. So substituting 1 and -1, so here is -1 and then here is 1. So 1 is equal to A, so we have the square root of 1 squared plus -1 squared all square rooted. So this equals this. And we know that this will give us square root 2. So 1 squared is just 1, -1 squared is also just 1. So we have 1 plus 1, which will give us 2. So we have square root 2. So right away you can see the correct answer is C. So looking at the solution here. So yes, so they do the magnitude of Fi, so the magnitude of 1 minus I. We have defined values of A is equal to 1 and B is equal to -1. Substitute in, get square root 1 plus 1, and then square root 2. So the correct answer is C. So the proposed solution is correct. Okay, so just clearing the board. So for our next question, we're asked, express the limit as a given interval. And then we have the limit of n as it goes to infinity for cos xi over xi dx, so delta x, from pi to 2 pi. So I'll just write out what's given. So we have the limit. We're essentially converting a Riemann sum into a definite integral, and we're kind of trying to relate those two. So the general format for relating them is the limit as n tends to infinity, where the sum from I equals 1 to n f at xi delta x. So this is equal to the definite integral from a to b f at x dx. So here we're given pi and 2 pi, so we know a to b is what we're defining, and here a is equal to pi and b is equal to 2 pi. And from the format of the equation that we're given, so we have we're given this component right here, which is what we care about to convert into the integral. So we'll write that out. So we'll say the limit as n goes to infinity for the summation I equals to 1 n, and then what's given to us is cos xi over xi times delta x. So we know that this right here is our f at x. So to give the definite integral, we know it's from pi to 2 pi. And then f at x will be cos x over x. So I'll just put this in brackets. And then we have dx. So this kind of converts the Riemann sum just from observing the terms in the Riemann sum and relating that to a definite integral based on this standard formula. So this is kind of the formula that you need to know, and kind of using this template, we're able to derive the definite integral, which is this, and that's our answer. So looking at the solution, they define similar integrals, and they come up with the correct definite integral. Yeah, so I'm just double checking that we answered the question. So that's the correct answer. So this question is making kind of just system with 3 equations and 2 variables must be inconsistent. So we're kind of asked for whether this statement is true or not. So think of it as a true or false question. When your system with 3 equations and 2 variables must be inconsistent. So we can kind of just start off conceptually. So if we have 2 variables, let's say these variables are x and y. So we have x and y, and we have 3 equations. So it could be any equation in the form of y equals mx plus b. Okay, so these are kind of, it will be different variations of those equations that are given to us. And it's asking if we're given 3 equations and 2 variables, is the solution always inconsistent? Because it says must be inconsistent. So here we have to define what inconsistent means. So to give you a general definition, so there's 3 terms that you should know. Inconsistent, inconsistent. Let me just make sure the 2 variables that I wrote up top are on the screen. So we have x and y. Okay. And then we have dependent. And we have consistent. So these are 3 terms that give you kind of the relationship between any set of equations. So the first term, inconsistent, this refers to no solutions. So if we were to solve a set of equations, so we have no solutions. If we were to solve a set of equations and variables for the variables, we would get no solutions. When the system is dependent, we would get an infinite number of solutions. So this could be represented by 2 lines just overlapped on top of each other. Those will give us infinite number of solutions. And when there's a consistent system, that means we get 1 unique solution. So we have 1 unique solution if it's a consistent system. So we've given the definitions for what each term means, and we're trying to figure out, will this scenario always give us an inconsistent solution? So we can draw a plane and think about potential possibility for a system where this may not be true. So a simple example would be, let's say we had a point here, and we had 1 line crossing through it, and then I'll just label this xy. And then we had another line crossing through over here, and we had a 3rd line crossing through it. And they all cross at one point. So right away we can see that we're given, in this situation, in this conceptual situation, we have x and y, so we have two variables, and we have 3 lines. And each line is represented by an equation y equals mx plus b. So 3 equations, or 3 lines here, with 2 variables, so 3 equations, and 2 variables give us one unique solution based on this diagram. So this is just one example of how this statement is incorrect. So we can say right away that this statement is false. So this is just one scenario where this statement is not true. And an easy way to think about how to answer a true or false question like this. So looking at the solution, so you would say a homogeneous system of linear equation always admits a solution. For a non-homogeneous system of linear equation, take an example. So here they provide us with 3 equations, kind of the same system that we went through, and we got a unique solution. So here, through these 3 equations, each represent a line, and if we substitute them into each other, we would get the same solution of a unique solution, so a dot on the xy plot that all lines pass through. Alright, so this question asks us to determine if the graph is symmetric about the x-axis, the y-axis, or the origin, or the equation r equals 2 cos 5 theta. So there's 3 tests that you need to do to determine if it's symmetric on the x-axis and y-axis and the origin. And these tests are as follows. So test for symmetry on the x-axis, we'd have to figure out if we substitute theta into the equation r, and we substitute negative theta, these two must be equivalent for symmetry to occur on the x-axis. The other situation that we could also solve for that would give us symmetry on the x-axis is so negative r theta should equal r pi minus theta. So this is the other situation that you can substitute in. So this one might be easier because it's just substituting in a negative value for theta. So this is for x. For y, for symmetry on y, we would substitute r into theta and theta into r, and then we would substitute r pi minus theta. So here we have r theta has to be equal to r pi minus theta. If we substitute pi minus theta into the equation, these two have to be equivalent for us to get y-axis symmetry. The other scenario that they have to be equivalent to is, not have to be, but one of them has to be true. And one of these two equations has to be true for symmetry on the y-axis, is negative r negative theta. So this is the other equation that we can use to test. So we're going to be using this equation to test for the above. And then finally, the origin we would test for r theta is equal to r theta plus pi. Or we could also test for r theta is equal to negative r theta. Okay, so these are what we want to test for to determine if it's x-axis symmetry, y-axis symmetry, or origin symmetry. So we're going to erase all this to make some space. Okay, so we'll start off with y-axis symmetry. So if we had r theta, we would just get the above equation. And then if we had negative theta, we would get 2 cos negative 5 theta. So here we want to think about the cos value, the cos component. So we know that cos of a negative theta is equal to, so let me just write this side by side. Cos negative theta is equal to cos theta. So this is just a definition of cos theta. So cos negative theta will equal cos theta. So knowing this, we know that therefore this must equal to 2 cos 5 theta. And therefore, because r negative theta equals r theta, therefore we have x-axis symmetry. Okay, so we tested for the first case and we know that we have x-axis symmetry. So here I'll just make a little legend and we'll say x check mark. And then the second scenario we want to test for is y-axis symmetry. So here we want to test, so we know r theta will equal this. So r pi minus theta will equal 2 cos 5 pi minus 5 theta. So here we can see that we can't really simplify this easily to get kind of both sides to be equivalent. We could try to expand this out, but we can kind of make a judgment call here, and you can see that this can't be really simplified into 5 theta because we have the extra 5 pi term here, so we know that there's no y-axis symmetry. So there's no y-axis symmetry. We only have x-axis symmetry so far. Now the last thing we want to do is symmetry around the origin. So symmetry around the origin is r theta has to be equivalent to r theta plus pi. So we know that if we substitute into theta plus pi, so the simpler way to look at this, if we're substituting into the cos term, so we really only care about if cos is equals to cos theta. So this is the kind of what we're looking at. So when we substitute r into theta plus pi, we would get 5 times theta plus pi. But here we really only care about this term. So this would be equal to, because we have the pi term, would equal negative cos theta. And that's really how I should have tested for the y-axis symmetry as well. So because it's equal to negative cos theta and not cos theta, that's why we get the no y-axis symmetry and no origin symmetry. So even if we substitute for pi, we're testing for the y-axis, for theta minus pi, we'd still get negative cos theta. Oh, sorry, this is a little messy. So we still get negative cos theta for both the y-axis, so this is the y-axis symmetry test, and then this is the origin symmetry test. We can include the 2 in the front, but 2 doesn't really affect it, and the 5 also doesn't affect it, so really we only really care about the angle in the cos component, and we know that it's only for x-axis symmetry. So here we only observe x-axis symmetry for the presented equation. So just looking at this solution a little more thoroughly. So x-axis then is satisfies condition, so it's correct. They test for this condition. So here, yeah, they ignored the 5 and the 2. You only really care about the cos negative theta to get cos theta. So you know that r theta equals r negative theta, and you have x-axis symmetry. And then they test for the y condition. So similar idea here. We have pi minus theta, substitute in, and you only really care about the cos component in the angle. And then this would give you negative cos theta, which means it's not equivalent. The two terms r theta and r pi minus theta are not equivalent. And then similarly here, same idea, we're only really focusing on the cos component, and you get a negative cos. So solution is correct. So which term is the perfect square of 3 times 4? Okay, so perfect square of 3 times 4. So it would be 3 times 4 squared. So simple enough. And then we can expand this out. So we can do 3 times 4, which would give us 12. And then we get 12 squared, which would give us, so if we did 3 times 4, it would give us 12 squared. And 12 squared was 144. We could also do it in a different way. We can do it similar to how the solution presented here is doing. We could do 3 squared times 4 squared, which would give us 9 times 16. So depending on, maybe this is a multiple choice question, and depending on what kind of solutions you're provided for, it might be in this format, or it could be provided in just the final solution, which is 144. So 9 times 16 is 144, which is equivalent also to 12 squared. So here they present the correct answer. Correct. Okay. Okay, so in this question, which polynomial is represented by the algebra tiles? So there's an algebra problem, and we have to find which equation here that represents these tiles. So we can kind of just start off by counting how many tiles we have. We have 3 values. So we have x squared, we have negative x, we have negative 1. And each one, the first one, we have 2. So we'll say, we'll use a dot to represent multiplication, and then times 2. So we have 2 x squared components. And we have 4 negative x components. And we have 6. So here 1, 2, 3, 4, 5, 6 negative 1 components. So going through, this would give us 2x squared. This would give us negative 4x. So equals, and then equals negative 6. And then we can just add all these 3 terms up, and we get 2x squared minus 4x minus 6. And looking at the solution here, so yep, they count the right amount. We get 2x squared, so they picked option A. Let's see what option A is. So yes, we have the same as option A here. So option A is the correct option. Okay, correct. Okay, so that's all we had time for today. Hopefully you found this session helpful. And if you need any more help, you can always visit in the description below or go on OneClass.com for any homework help or tutoring needs. See you in the next session. Goodbye.